Okay, today we're going to have to compute the I gross for this section. We're going to find out the I cracked and the I gross, and then we'll be able to find deflections for this section. So we're carrying on with more design checks today. But this is to find deflections. It takes quite a lot of work. So we're going to do it in a few stages. So first of all, we've got to find the modular ratio of the section, and we know that the E of the masonry is 850 times F prime M, so that would come out to be 8,500 MPa, and the E of the steel is 200,000 MPa. So the N value would be 200,000 over 8,500, and that would give 23.5. So N equals 23.5. So now we can find out where the neutral axis location is. But first, let's get the transformed area of this top and bottom steel. So this steel would be N minus 1 times the area of steel. And in the example, it was 500 millimeters squared in the bottom steel. So N minus 1 times 500. 23.5 minus 1 times 500. So this AT of the steel would be times 500, 11,300 millimeters squared. And then similarly, we do the same thing for the top steel. And the top steel was 115 M bar, 200 millimeters squared. So the AT prime would be 200 millimeters squared times, I kind of reversed it, but 200 times N minus 1, 23.5 minus 1, which comes out to be 4,500 millimeters squared. So let's start and find the centroidal axis of the section. And this, again, this is for gross section, uncracked. So all the concrete is, all the masonry is totally effective. Okay, so the area of the masonry is 190 times 590, which equals, let me see, that's 112,300 millimeters squared times the distance from its centroid to the base, so times 590 over 2 times 590 over 2, that's 33.1 times 10 to the 6. So that's the Y bar A for that component. Then the area of the top steel, 4,500 millimeters squared times distance from here to here. So that's going to be 590 minus 60. 4,500 times 590 minus 60. 2.39. times 10 to the 6, and then similarly, the bottom steel, 11,300 millimeters squared times this distance, which is 60 millimeters. Right, 590 minus 530 is 60. So 678 times 10 to the third So now we can add up the areas, the sum of the areas. 112,300 plus 4,500 plus 11,300. 128 times 10 to the third millimeters squared, and then the sum of the y bar areas, these 33.1 e to the 6 plus 2.39 e to the 6 plus 678 e to the third, 36.2 e to the 6. And that's millimeters cubed. So the y bar for this section will just be the y bar areas, 36.2 times 10 to the 6 divided by the area is 128 times 10 to the third. So 36.2 e to the 6, that's the answer, divided by 128 e to the third, 283 millimeters. So somewhere around here we'll have the neutral axis location, and that's going to be 283. Great. Now we can find out what the inertia of the section is, the I gross, and we'll break it up into components, and we'll take our 80 squareds about the base and use parallel axis theorem to bring it to this neutral axis. Okay, so let's start with the masonry. It has inertia 112 times the base 190 times the height cubed. So that's going to be 590 cubed times 190 over 12. 3.25 e to the 9th. And then the 80 squared would be, the area of the section is 112,300. And its d squared would be half of 590, right? The distance from mid-centroid to the base. Squared, 80 squared. So that's 112,300 times 590 times a half squared. 9.77 e to the 9th. And then the top steel, that has an area of 4,500. And its d squared would be 590 minus 60 squared. So that's 4,500 times 590 minus 60 squared. 1.26 e to the 9th. And then the bottom steel, that's 11,300 times its distance to the base. So 530 minus 590. This distance is 60. So 60 squared is the 80 squared. So 11,300 times 60 squared. 40.7 e to the 6. And then we'll use parallel axis theorem and take the whole area, 128 times 10 to the third, times the distance from the inertia, we calculate the inertia about this bit.